First is mechanics. First, we're going to talk about conservative forces. First, we want to talk about the different categories of forces. Biggest categorization is conservative versus non-conservative forces. For a conservative force, the path the force takes on an object does not affect the work done by that force. But in a non-conservative force, it does. So some examples of conservative forces are electric force, gravitational force, elastic force. And other examples of non-conservative force are like friction, applied force, tension. What does this mean? Well, what it means is whenever you apply a force on an object or a force is applied to an object, that force does work on the object. What conservative forces means is that no matter what the force, like which path the force takes, whether it takes this red straight line, whether it takes this curvy green line or this blue path from point A to point B, doesn't matter. The work done is the same regardless of which path you take. Whereas obviously, if, for example, applied force is a non-conservative force. Applied force is when you like push something. So if you took object A right here, then you pushed it to point B using this red path, that would you would be exerting a certain amount of work. You'd be doing a certain amount of work on object A, right? Well, if you, instead of pushing the object down the red path, if you instead pushed the same object, object A, this way on the green path, and you did all of these unnecessary curls and whatever to get to path B, you'd be actually doing a different amount of work, right? It, obviously, as you would expect, be a little bit harder, and you'd be actually doing more work on the object in order to get it to move, because you're actually moving longer distance. Same thing with if you took path C. So a non-conservative force like the applied force or like the tension on a string or like friction, it depends which path you take to get from A to B. Whereas something like gravity, it doesn't matter which way you go, it's the same amount of work being done regardless. Okay, so that's just an important distinction. Next, we want to talk about point-object systems. A point-object system is any system where the object we are looking at is represented basically by a point in space. And you've been using point-object systems probably without knowing it in physics your entire college and high school career. And the reason is because when, for example, if we were to find the total energy of an apple mid-fall from a tree, well, if it's falling, you know that what energies are acting on it. Obviously, it has kinetic energy because it's moving. It has a velocity, so it has kinetic energy, and it has height, so it has a potential energy, right? That's what makes up its energy. So you would just draw a diagram, kind of like here. I'll draw it. The apple's right here. It's falling down from a tree. It has a certain, here's the ground, has a certain height. The object has a certain mass and has a certain velocity as it's going down. Things like that. G is 9.8, whatever, right? And notice how in this drawing, I drew the apple as a dot, a point, right? That's because if I drew it instead like this, bear with me, this is like a real apple, right? Then you kind of have to figure out like, okay, does it maybe rotate a little bit as it's falling? And where's the center of mass located? How does the shape affect the way it falls? Maybe the shape gives it some rotational energy, or maybe like slows it down or something like that. Maybe there's some kind of other factors in play if it's like apple shaped, right? So to make things simpler, we just treated any object, no matter what it is, like an apple, a water bottle, anything, a car, we usually treat it as just a point in space, like a single point, right? And we don't take into account that like the shape. So if it was like a car, we don't take into the shape and like where its center of mass would be. How does its like aerodynamics affect it or something like that, right? That just makes it a lot more complicated than we can solve. And so one way that we actually, like in real life, when you're doing physics and you're doing like models, like maybe in MATLAB or in some kind of CADing program, you'll obviously have to work with like real objects, and you'll have to find all this information out. But for the MCAT, it doesn't matter. If like for simple physics, we use point objects, okay? Next, going off along that, we also have to learn about the center of mass. For simple objects like a sphere, center of mass is exactly the middle of the sphere, right? Makes sense? As long as it's like a uniform sphere, it's in the middle. But for more complex objects in systems, that's not the case. Like, for example, I have a water bottle here. What's the center of mass in the water bottle? It's not going to be exactly in the middle of the water bottle. It'll be somewhere else, especially in this water bottle where it's only half filled. Right? If I put it like this, it's a different center of mass. And if you have a car or like a person, right, it's a different center of mass. So in a system that has multiple masses, right, the equation is as follows. And this equation doesn't come up too often, but this is the equation for center of mass. So x center of mass, cm is center of mass. So the location of x is like the location. The location for the center of mass is equal to the mass of object 1 times the location of object 1, mass of object 2, location of object 2, and then so on, mass 3, location 4, whatever, right? And then all of that divided by mass 1 plus mass 2, mass 3, mass 4, whatever, as it goes on, okay? Let me show you a picture of that. This is what like a simple system of masses would look like. You have this one small mass right here, this big mass right here, and you have to find the center of mass. Well, the x is the location, like I said. So the location of the center of mass, location of 1 times m1, location of 2 times m2, and you do this formula, and then you find the center of mass somewhere here, right? You can see it's not exactly in the middle between them, but because they're different masses or something, right? Yeah, this is probably as much as you'll see on the MCATs, like simple points, again, points, and that have masses. That's how you make a system to get a center mass system. In real life, if you had something like a water bottle or like an apple, what you would do is you would pick different points on like the apple or on the water bottle, like a bunch of different points, and you'd have an algorithm that determines the center of mass between all of those different points. And it's like kind of like an integral, and you can use actually integrals to find the center of mass of an object like that as well. But most programs have like a built-in algorithm for that, and you'll just have a system with many different masses in like a water bottle, and then using all of those, it'll kind of construct where the center of mass of a water bottle or a person is. Okay, but I really doubt they'll ask something like that. Most they'll ask is like simple points like this. Okay. Next, we're moving on to the work kinetic energy theorem. This theorem is used to relate net work to the change in kinetic energy. The equation is net work equals 1/2 mv squared final minus 1/2 mv squared initial, right? So essentially, this can be rewritten as, I'll write it here, work equals delta Ke, right? Work's essentially equal to the change in kinetic energy. That's what the network is equal to. If the network is positive, then the final velocity is greater than the initial velocity, and kinetic energy increases. If the network is negative, the kinetic energy decreases. Network is 0, there's no change in velocity, right? Because mass of the object, assumedly from the start to finish, stays the same. 1/2 is 1/2, and then the only variable is v. Very simple. Just remember, work and kinetic energy are very closely related using the equation work equals delta Ke. Okay. Last thing we want to talk about for mechanics is mechanical advantage. So we often in real life use tools to do work for us that would be impossible otherwise. Like, for example, we use levers or pulleys, which we can put minimal or lower amounts of force into, but they yield a much higher force on the other end, right? If you had like a car jack, you obviously can't lift a car, but if you just press down on the car jack, it can actually lift up the car enough, right? Because it's a lever system, and when you press on it, it can output much more force than you can input. And this is called mechanical advantage. There are 6 simple machines that we are used for mechanical advantage: levers, inclines, pulleys, wedges, screws, and wheel and axle. They each have their own formulas, which you don't have to know. in terms of how they kind of like convert things. Like mostly it's based on like length and things like that. That for like wheel and axle, like diameter, and like it has a lot of different things. That's way too specific and too complicated for the MCAT, so you don't have to know them. But the formula that you should know is that mechanical advantage is a ratio of output to input. Thus, mechanical advantage is equal force out, O is for output, over force in, or input, right? So however much force you get out divided by how much you put in, that's the mechanical advantage of the certain machine or system. There's just a diagram of what it looks like a lever, obviously like a seesaw or like a car jack, something like that. Pulleys, screws, obviously wheel and axle, inclined plane, wedges, right here.